But yeah, an additional point of view on what I just discussed before the break. So really, this is the core difference between the perspective neutral approach and really all other approaches. And particularly in the notion of invariance, the core difference with these three other approaches that I mentioned there. So let's think about this from the point of view of equivalence relations. So that I already mentioned, kind of in some sense. So one thing is, so I wanted to keep some of this stuff written here that I can point to it, but I do need some space to write. So I'll squeeze it in here. So here, I had chosen psi1 and psi2 in such a way that they're actually related by a gauge transformation there. You can check that, for instance, G of psi1 is equal to G of psi2. Okay. It's not very hard to check. So, the difference here is just that psi2 is equal to psi1 up to this conjugation by a gauge transformation. But then, when I do the G twirl, I can absorb it into these U's, and then just by the invariance of the H measure, just redefine the integration variable. So it means these states here, they're in the same equivalence class of states of kinematical states that map to the same state that is invariant in this weaker sense. And so really what we're doing is with a G twirl is that you can view this, I'm going to write it somewhat loosely, you can think of it as H kin, okay, let me write this in a somewhat more, let me write S of H kin, so I mean by that the density operators or density matrices over the kinematic Hilbert space, and you're going to map it to, let's see if of H kin by an equivalence relation. And really, the equivalence relation is that psi is equivalent to psi prime if and only if there exists some G such that psi equals U of G psi prime. Okay, so that's the equivalence relation. So if I have two states that are pure states that are gauge equivalent, that are related by a gauge transformation, I'll consider them equivalent. So that's the equivalence relation I have here. And basically, by the argument that I just made, it's clear that G is consistent with that equivalence relation. Now the thing is, so I can think of, an equivalent class of such states. But one thing is that the space of equivalence classes has no linear structure. Okay? So this is not actually, the space of states that I get in this way is not a Hilbert space. It's not even a linear space. So, so the space of these equivalence classes is not linear. So there's a priori no way in which you can do something like psi equivalence class, A B, and then you take some different equivalence class. So this, okay, maybe I shouldn't call this psi prime here because it's not supposed to be equivalent. We take some other equivalence class, and in general, I cannot define that operation, or it's not clear what that's supposed to be. Because in practice, you would want to say, well, I'm going to, I take any member of this equivalence class, and any member of this equivalence class, and then I just add them up. But the point is that the result of this addition for different members of representatives here and different representatives here, I will get a different result at the end. They will not, and when I say different result, these different states that I get afterwards, they will not lie in the same equivalence class. So that's why there's no linear structure. So, so really, in order to make this consistent, I need an additional condition. So to get, so this here is basically, this makes no sense. So okay, the reason being, I mean, maybe, I don't know if that's came across what I just said, if it was clear, but basically suppose we pick, here in this one we can pick, let's say we have psi 1 in there, and we have psi 2 in there, so that means they're related by a gauge transformation. So if I then do something like A psi 1 plus B, and then I have some phi, for instance, and I do A psi 2 plus B phi, this is not going to be the same in general. It's not even under equivalence relations, because what's the difference here? So if I take these two states, when I look at the difference, delta psi, so here, okay, what are we going to call this now? Sorry, let's call this capital psi 1, and this here capital psi 2. So if I look at the difference between the two, of course it's just A times psi 1 minus psi 2, right? And so this is something where I can write it as 1 minus some u of g times psi 1, right, by using the equivalence relation here, right? And now the thing is that this state here, so if g is non-trivial, this thing is not gauge equivalent to 0. Right? So I have a, if g is a non-trivial operation, so g is not the identity, then this is a non-trivial unitary here. This is a non-zero state, so it's a non-zero state, and a non-zero state is never unitarily equivalent to 0. So this tells us in particular that, okay, this is getting really messy, I'm sorry, but I guess I don't need this here anymore. So this tells me that, you know, the delta psi is not gauge equivalent to 0. And so this tells me then, you know, that psi 1, the equivalence class is not equal to the equivalence class of psi 2. This here. Okay, so so this tells you already that it's an example where you can see that you know, doesn't conflict with defining the linear structure. So, but also this example kind of makes clear what we have to do, which extra condition we have to impose in order to get a linear structure. So what we have done here is we have said, okay, we're going to identify psi and psi prime in an equivalence class if they're gauge related. But now what we see here is we're still allowing that the difference between two states that we identify, that it's non-zero. So it's a bit at odds with really having a full indistinguishability of these states. If I want to have a full indistinguishability of these states, I should also require that the difference between two gauge-related states is indistinguishable from 0. So I should identify it with the null state. So that's the difference really between these two ways of doing things. Okay. So this one requires only this equivalence relation. The stronger sense is it requires this equivalence relation plus requiring that the difference between two gauge equivalent states is also equivalent to 0. But when I say also equivalent to 0, I don't mean gauge equivalent to 0, because clearly it's not gauge equivalent, it's a separate, it's an additional equivalence relation that I'm imposing. Okay. So to get linear structure, we need that 1 minus u of g psi. I'm going to write this as a different equivalence relation with a hat. That this is 0. So it's in addition. So let me say also. Okay. And now, so
what do you mean by hat?
Well, I just want to distinguish this equivalence relation from that one. It's a different one because this one does not imply this. So that's what I was trying to emphasize here. Here up to here, I've only used the first equivalence relation, and I get that this delta psi here it's not 0 because it's not gauge equivalent to 0 because this is when this is a non-trivial operation. This is a non-zero state, and I mean, a non-zero state is never going to be unitarily equivalent to a null state. So this here is more than that. It's not. This here is not an equivalence in any unitary sense. I'm just. It's a separate equivalence relation that I'm requiring, and that's why I'm putting a hat to distinguish it from the other one. But if you have this realized, if you have this and this realized, then on the equivalence classes that I get by using both of these equivalence classes, then I have a linear structure. That's a Hilbert space. And then now the thing that you can easily check is that this is exactly what this here does, because when I do pi pn, and I take 1 minus ug, and I have some psi, this is exactly 0. So this is what the equivalence class that I get from coherent group averaging. Okay, so this you can see from, this is dg prime ug minus ug prime minus ug prime ug psi, right? But then here I'm just going to do another relabeling of the sum, and I use the invariance of the H measure. So this thing is equal to that thing, so it's 0. So in this way you can see that this here is coherent group averaging, this is incoherent group averaging, and the incoherent group average corresponds to taking equivalence classes that require gauge equivalence in the unitary sense, plus the condition that the difference between two gauge equivalent states you can also not distinguish from a null state. Okay? And this is really the key distinction between the perspective neutral approach and the rest. And this is a much stronger sense in which you're independent of the external reference frame, because not only are you identifying states that are related by an external reference frame transformation, but even the difference between them you can't distinguish. So that's why, in this sense, you can really say that these other approaches are not fully external frame independent, because they can still distinguish the difference between two states. They can't differentiate, they can distinguish from 0. And that this is non-zero, that these states here are not mapped to 0. You can also see, for instance, here, in this example here that I considered, I only need that A and B are not 0. I can set B to be minus A, right? So then here I have exactly the difference between the two. And so I'm actually looking at exactly this delta psi here. And we've already seen that this doesn't give you a 0. Okay, so this is another, I think, useful way in which you can think about the.
You said quantum information approach or other approach, they impose only the weaker condition.
Yeah.
So how that approach overcome this problem?
Yeah, it doesn't. I mean, well, okay. So I should say these two approaches don't overcome this. I mean, the thing is that at the end of the day, so they only work with this G-twirl, and then you get these incoherent states that are gauge invariant in this weaker sense. But the point is that generically the states that you get this way are going to be mixed states, so you have a convex set. Okay. So you can still have convex linearity, but you don't have an exact linearity. So it's not a Hilbert space, but it's a subset. I mean, it's really, okay, I think I wiped it out at some point. Well, okay, maybe it's this here. And you still have, density operators. You have the subset of density operators that are gauge invariant. It's still a convex subset. So in that sense, operationally, it's still okay. It's just not a Hilbert space. And in the operational approach, okay, they do some additional stuff where they impose some other kinds of equivalence relations that are whether or not you can distinguish states with access to these or those observable algebras. That is separate from what I'm discussing here. And then in some cases you can generate a linear structure and so on, but it's not really, typically you don't get a Hilbert space there either. But again, because it's also the idea that this is an operational approach, I mean, that's, in principle, operationally, it's okay if you have just a convex set. So it really depends on what you want to do. So this is not to say that this is wrong. It's just I'm just emphasizing what the key difference is between the two. Okay. So yeah, I think that's all I'm gonna say about this. So now the question. So I wanted to tell you a little bit about how you go about now implementing this invariance in the stronger sense. I claimed that I would do this yesterday. I'm starting to think that I may not do a lot of this because otherwise I will not really get to any kinds of applications. I was hoping I could start discussing von Neumann algebras today and these observers and relational entanglement entropies and perturbative gravity using the formalism that we've already developed. But since I will have to tell you something about von Neumann algebras, that will take time. I mean, I have time to back up all the claims I made so far. So anyway, so this here is the, this is really a perspective from the slide. Okay. Okay, so yeah, maybe let me just say this because the construction of HPN. So there's at least two equivalent ways in which you can do it. So there's two equivalent ways. And one is called the co-invariant method. And the second is really, it's called refined algebraic quantization. So both are really an implementation of Dirac constraint quantization. So, the second one is essentially taking constraints and looking for the null space. And the first one is essentially what I just described before, is taking equivalence classes. Okay? So it's by the equivalence classes or equivalence relations introduced. So you're going to identify states if they're gauge related, and then you quotient the resulting space by this additional the null states that come from this hatted equivalence relation. Okay, so so this gives a linear space. It's a complex linear vector space And in order to turn that into a Hilbert space, I have to define an inner product on it and then complete in the norm of that inner product, so the Cauchy completion. So yeah, the linear space is the space of equivalence, like double equivalence relations. So to get HPN, we need an inner product. And the point is, again, we're just going to define it by what I already told you before. So I take round brackets again. And really it's just, and just write DG psi kinematical, then UOG y kinematical. For this here, the angle brackets are again the kinematical inner product. So as in this previous example with the particles that I gave you. And once more, these psi kins a priori, they lie in the equivalence class under this one here. So any member of an equivalence class related by this, I can stick into this. And any one of them I can use in the definition of this here. And then, this here I can essentially, so assuming I can put the integral inside, which often is done, then I just get, again, this thing that I had written down before, and we already know that from what I explained here, that what I consider as the null states in this construction here is actually literally mapped to 0 by πpn. So you see then that that states that I consider as null states according to the second equivalence relation, they literally are null states of this inner product. So this inner product is actually consistent with that. So this is consistent with null states. So here, maybe I put a star here, and it's this star, and I'm referring to this relation. Okay, so now this is a candidate inner product. So we have a candidate inner product. And I say candidate inner product because for it to be a proper inner product, we have to guarantee a couple of things. So we have to have reality conditions satisfied. It has to be positive, semi-definite, and in particular, the group averaging that we have here has to converge. And so that's not in general guaranteed. Okay. So in general, it's unknown whether whether this converges, so the group average, whether it's positive, and whether it satisfies reality conditions. So by positive I mean if I take psi that it's greater or equal, greater or equal to 0 if psi is not a null state. So so you can look a little bit more on this by there's some work. I mean, Don Merrill has written a lot of stuff on this. So really, it's 90s plus. There's also Merrill plus I think Morrison. It's something, I don't know, something 08 or 09 or something like this. In fact, also some more recent works by him. And okay, there's also Giulini, Merrill, something like 95 or something. You can check. Where they discuss this. So there's many cases where this actually works, where you can prove that it works, but the completely general case it does not know. So, and there are some counterexamples to this. So even in the Zitter space, in some special setups, you can show that it will not converge, and that's, for instance, in some papers by Merrill and Morrison. But generically, in the known examples, it works. So, so that's just to emphasize that in constructing this Hilbert space, there's still, in the completely general case, there's unknowns there, and it's an open technical problem. It's not a problem per se for, of course, the perspective neutral approach. It's just a general problem for constraint quantization of gauge theories. It's a challenge that has to be solved still on the mathematical side. So here, that means we're just going to assume this inner product exists. Okay. We can't do anything else at the moment. So, so that's the best we can do right now. So again, there's many cases where it does work. And I think, yeah, so for compact groups, there's no issue. I should say that, of course. So for compact groups, this PyPN is just the standard projector. So the troubles are more for non-compact groups. And then, for instance, one other thing is that when the representation, so I think this is also shown by Merrill and Giulini in this paper, for instance, if the representation is a regular representation, I think that you can always make this work, for instance. So even when the group is non-compact. Okay. So anyway, and then completing a norm, and then we get this Hilbert space. We can think of it as a Hilbert space of equivalence classes. And now, so this is the first method here. And this is also the method that Winton and so on recently used in their construction of observers in conservative quantum gravity. It turns out to be directly equivalent to and it's equivalent to directly solving U of G psi in the distributional sense. So I was going to discuss this a bit more, but I'm not going to do it. So this here is the more standard way that many people are familiar with, that you take your constraints and you set them to 0. Then, of course, again, when it's a compact group, it's clear what to do. It's more that when the group is non-compact, then the solutions to the constraints are not, I mean, as in this example that I showed you, with the 3 particles on the line, where the constraint was the total momentum. The physical states are 0 total momentum eigenstates. They're not, they're distributions on the Hilbert space. They're not part of the Hilbert space. But then it turns out that this inner product one uses both methods, and that's ultimately also the reason why it is equivalent. And yeah, so this is somewhat more commonly used in the canonical quantum gravity community, for instance. Yeah, so there is, I mean, this is actually not so well known that they're equivalent. So there is, so we showed it for Hamiltonian constraints in a reference that I can give you the notes. Still loading details for Hamiltonian constraints. In 24, oops, 12, this one's not loading. So for Hamiltonian constraints, you can look a little bit in there why these things are equivalent. There's also some recent work by Henry Maxfield and Jesse Helds from like 2 weeks ago, where they do it for the same kind of cases as we did in there. Okay. So I'm not going to get further into this. So I hope that gives you a little bit of an intuition of what the the differences to these other approaches are and what the basic ideas are for building the Hilbert space. Okay, so now I have, when do we start? 1:30, so I have about an hour left. So I think there's maybe some statements that I should prove for you that I made, maybe in particular that this reduction map is unitary. Yeah, let me maybe, so I'm gonna, a few details of what I mentioned I'm going to back up, but not. So one thing to note, I mean, I'm just gonna do the claim. So we take pi pn, we take one reference frame. So this is a technical lemma. Yeah, you could call it a lemma if you want. Pi pn, this is pi pn for a unimodular group. Okay, by the way, one reason you may wonder why do we take a unimodular group? One thing is, maybe I should say that. It also has to do with these inner products actually. So so this is a bit of an aside, but since I'm throwing around these unimodular things, and you may wonder why the hell I'm doing that. So this is a bit of an aside. So why unimodular G? And so again, remember it means that the H measure is both left and right invariant. And the thing is that if I look at pi pn dagger, so this is dg, g, u of g inverse. Okay, so I'm just using here that u of g dagger is ug inverse because I assume that's a unitary representation. But this is pi pn because dg is dg inverse. Okay, so this is for unimodular groups this is true. Now, for non-unimodular, this dg is not equal to dg inverse. And so you will not have that pi pn dagger is equal to pi pn in this sense. Okay? And so then, when you want to define inner products and so on using this object here, then you have to do some extra gymnastics. So in these works by Giolini and Marov, in fact, there's also some description about what you do when the group is non-unimodular, but the point is that in that case, you cannot have a unitary representation or use a unitary representation of G and have a notion of invariance of states. So you have to change the notion of what you mean by invariance. You have to add phases and so on, and that makes life a little bit more complicated. And I don't want to go down that route.
So in the last line, you mean the dagger is not equal to the original?
Well, for non-unimodular.
Yeah. So, but you are writing equal, right?
Oh, yes.
Sorry. Yeah.
Yeah. Important detail, yes. Okay. So now, why is this true? Proof. So we can look at. So one thing is that we can look at in general for some operator. So we have pi pn. That this is pi pn a pi pn. I don't know if I proved this before, but it's kind of very simple to see because this here is it's dg u of g a u of g dagger pi pn. But then remember that this is gauge invariant here. I can just absorb that inside. So this here is just pi pn. Is that clear? So because it's in the image of the invariant. So is that clear? Okay. So then, you know, when I have this, then well, this is also just pi p n. Right? So that's why this is true. And now, and we have that. IS. So now we set A to be this object here. Okay. So then, well, this is this GG prime, and then I have phi G prime G, phi G prime G, are tensor IS, right? So I mean the gauge transformation, the U that sits inside the G twirl that acts on the system is just getting cancelled because there's nothing on the system, right? So I'm using that the U that sits inside here, you know, these U's that they have a tensor product representation. That's what I'm using. But you know, now again I'm using the invariance of the H measure. I'm just going to call this now G tilde, and then I can just change the H measure to G tilde, and then it's nothing else than the resolution of the identity that I used in the requirement of the covariant POVM. So this is IR IS, and this here is by the resolution of the identity for the coherent state system. So in this way you see that the coherent G twirl of this conditioning operation is the identity. And so, and then using this here, so inserting this in here, then it's clear that I get that result. So that's the first thing. Okay, so then the next thing we need for unitarity is I'm going to call this, I think in one of the papers we call it pi s phys g, and what I'm going to do is phi g off the frame. So I'm taking the sort of partial matrix element of this group averaging projector in quotation marks in the reference frame. So you know there's still an operation on S left, right? So I'm only conditioning out the frame part. And now the claim is also that pi s phys of G is an orthogonal projector. Okay, what you can immediately see is that you know, pi s, so proof. So if I dagger this, it's clear that I get same thing back. Formally, of course, pi s phys of G. I'm not doing anything here for unimodular groups, of course, because I'm using here that pi p n dagger is pi p n. And now we want to take pi s phys G squared to see that it is really a projector. So we'll have phi of G, pi p n, phi of G, and then again phi of G, pi p n, phi of G. And now you can see why I wrote down the first result here. So we just proved that this here is pi p n. So we get that this is pi s phys of G. So here I'm using this result. I'm really going to only prove a small subset of results that you need to understand what we did. This is in order to show that the reduction map is unitary. So remember, we had that G, we just identity on S. And now, yeah, we can act. So I'm now generalizing what I did with the page-Wooders formalism yesterday. So I illustrated. So we can have psi s of g. We're just going to define it as the reduction of some physical states. So this guy here is in HPN. So remember yesterday I did this with clock states, and then I showed that this obeys the Schrödinger equation. So this is of course more general. So I can have, for instance, that psi s of g prime g. You know, since time is running, let me just say what it is. So it's really there's nothing else than psi s of g. So this is the generalization to general groups of the Schrödinger evolution. So the argument, I'm going to leave this as an exercise. The argumentation for this is essentially exactly the same what I did with the Schrödinger equation yesterday. You only use the covariance of the frame orientation states and the invariance of this, and then you arrive at this. It's very simple to see. Now another thing is, so this here is the, you know, this is the system S, sort of as seen from R's perspective. And I want to, so the reason I'm interested in this projector is, will become clear now. Because it is the projector onto the subspace of the kinematical system Hilbert space that's consistent with gauge invariance. So what we can do is, so I'm just going to sorry, I'm going to open another one that's right like this. So we have that psi s of g. You know, I have this feature here, so it is phi of g psi. Okay, so I'm dropping all these R labels here. In principle, of course, you need to have an R label there, but it's going to get a little bit cluttered. I'm going to insert now a resolution of the identity, GG prime, 5G prime, 5G prime. Sorry, no, not here. So I'm going to insert this here. So that means I can write this as phi of g, R, and then acting on dg prime, phi of g prime, R tensor psi s of g prime, right? So I've just inserted here a resolution of the identity, and then I made use of the fact that this piece here is just nothing else but R of g prime. So that's why I get this here. I'm just using that definition here. So I can write any physical state in this form, formally. And now, okay. Before I go there, let me add something here. let's write this in a slightly more explicit form because you will now see it over here. So what is this here? I mean, this is EG prime, and then I have phi of G. I have phi of G prime, G, and then I have a US of G prime. Okay, so I'm just using the definition of this pipe here. And so, and now we can make use of this here. So this means in particular, we have dg prime, phi of G, phi of G prime, R. And then here I can make use of this covariance and I can pull this out again here. So I can write this as US, yeah, why not? I can write this as US G prime. Does that help me with what I want to do? Psi S of E. Right. Yes, so now we're going to do a variable relabeling. We're again going to make use of the left-right invariance of the H measure. And we're just going to change variables where now we set G prime to be equal to, what do we want actually? We want G prime G. So, yeah, it's called G tilde. G. Where G is the fixed one here, and here I'm going to go over G tilde. So I have phi of G, phi of G tilde G, R, and here I have US of G tilde G. I keep the G tilde here, and the G I'm going to put back into here. So psi S of G. So what's the end result? This here, this whole thing that you see here, this is exactly that projector here. So what you see from this equation is psi S of G is the projector times psi S of G. So that tells you that that these reduced states lie in the image of that projector. So we have psi S of G is pi yeah, it is actually in this case psi S is of G, psi S of G. So that means the image of RG, or the act of pi n, so this is contained in pi S is write it in as HS phys, where this is just pi phys S of G on HS, where HS is the kinematical system Hilbert space that we started off with. Is that clear? So actually one thing that I didn't tell you is that in general, this projector will actually depend on the label G. So in particular, when the frame does not have reorientations, which is true, you can construct explicit examples of this. When this does not have reorientations, then you can easily convince yourself that that this projector will explicitly depend on G, which means also that the subspace that you're going to project into the image of the frame will lie in a G-dependent subspace of the system limit space. But these are somewhat exotic examples, typically, in particular for all abelian groups, all compact groups, and so on. This will be G-independent. Okay. Now, so the converse is in fact also true. So you can show that it's equal. The image is actually equal to that. But one thing that I still want to emphasize here is also that in general, this is a non-trivial projector. And in particular, it is a non-trivial projector when the frame is non-ideal. Okay, so when the frame is ideal, this is a delta function. And when there are reorientations, so for ideal frames, I should say there's always reorientations. It's the regular representation. This will cancel out. I will have an identity element in G prime here. So G prime becomes the identity by its delta function. So I collapse the integral to US of the identity, which is the identity. Good. So and this may be another comment. So for ideal QRFs, we have that pi s phys of G is just the identity of S. That's only for ideal quantum reference frames. So in general, it's a non-trivial projector. So that means not every kinematical system state is consistent with gauge invariance. And actually, a nice intuitive example in which you can think about is, again, Hamiltonian constraints. When you have a clock that is completely, with a Hamiltonian, it's completely unbounded. So let me maybe, so you have something like Hamiltonian constraint, HC plus HS. And now suppose this is a completely unbounded spectrum, so like momentum. It has every value of R in its spectrum. And it doesn't matter what the system is, you can always find a solution to this equation. Because for every energy eigenvalue of the system, I'll have an energy eigenvalue of the clock that is exactly minus the one of what I have in the system. So for every energy eigenstate of the system, there will be a solution to the constraint. So in that sense, so this remembers an ideal clock when it runs over all R, the spectrum. So this is, how you can see that. Suppose a system, a Hilbert space is spanned by the eigenstates of this guy. This is how you see that there is no restriction on the system energy eigenstates that are consistent with gauge invariance. Which is why for ideal clocks, the image of this projector will actually be the entire kinematical system, Hilbert space. But now imagine the clock is, for instance, a harmonic oscillator. You have a U1 periodic clock, and so it's only a harmonic spectrum that is allowed. And the system could, in principle, be a free particle. And that means I will not, for every energy eigenvalue of the system, will I have a corresponding minus eigenvalue of the clock that will cancel all this to get 0. So, and then this way you can see that then you will not have a solution to the constraints for every system state. So in that case, you will get a non-trivial projection. Okay, so this is part of what I need. And now I basically want to, just the one thing that I maybe want to show still is, so we have our R of G. Phi of G. And then I just claimed that our dagger of G is just given by this pi Pn. So I wrote that down when I wrote the quantum reference frame transformations. So I just quoted this. So now let's see that this is, I mean, here of course I'm taking them, sorry, I should say here as a map, of course, R of G as HPN to HS Phys, and okay, in general that would be, this would be G. So by R dagger, you know, I basically have to show that it's the inverse of this. Okay, one thing, well, this is unitary. Basically, the proof is immediate. So if I look at RG, R dagger, RG, what do I get? I have this guy collapsing with this here, so I immediately have that's pi S Phys of G. Okay, so this is the identity on that Hilbert space. Right? So here, R comes with this phi GR, and then I smash this onto this here, but that's just the definition of this pi Phys G over there. And we have RR dagger G, RR G, and this is pi PN phi of G, phi of G. So it's this here. But then remember that we had previously shown that pi Pn times this thing times pi Pn is equal to pi Pn. So that means that's the identity on the physical root space. Yeah, so it's unitary. So is that last step clear? So this also works for non-compact groups. I don't want to have the pi, I mean, I can't have the pi Pn here in general because for non-compact groups that's just going to give me divergence. But here in the last step, I'm just using what we had previously shown, what I have wiped out, that phi of G, pi Pn, that this is equal to pi Pn, so I had previously shown this. So you see that, you know, this is not in general the identity on the physical Hilbert space, only when G is compact. But you know, the image of this one is the physical Hilbert space. What that tells you is that this guy here is the identity on the physical Hilbert space. So that's why I have this here. So then from this you can immediately show that also inner products are preserved and blah blah blah. So I'm not going to do this specifically. I mean, it should be clear that this will happen. And okay, we have half an hour now. So I want to come to subsystem relativity now. Let me see if I prove another result. Let me first state it, and then I'll see will I prove it. You take your relational observables here. Okay, it's again, I take them on the physical, on the perspective proof Hilbert space. G. And I want to, so these are gauge invariant ones, and I want to gauge fix them. So I'm going to conjugate it by this map. And R dagger G. The statement is that this is pi Phys S of G F of S pi S Phys of G. So it's, you know, I had put in an arbitrary kinematical system observable, I gauge fix it to the projection of that arbitrary system observable that's consistent with the image of our map. So particularly what you can read out from this also is that these relational observables in general, they define equivalence relations. So if I have different kinematical, I can have different fs and fs prime. If they project under this thing to the same operator, then I will get the same relational observable here. So it's also a many-to-one relation. And in particular, as I noted before, if the quantum reference frame is ideal, this is a trivial one. So if the quantum reference frame is ideal, you just have fs. So, this S is identity, so it's just gauge fixing. So I mentioned this, for instance, this morning when I started, when I wrote the observable way of mimicking what happens in special relativity when I gauge fix. And conversely, let's call this here fs phys maybe, for simplicity. And okay, this is maybe that immediate, so if you take fs phys, you just conjugate this R G, and you get O fs R I. Let's see, maybe I'll do that very quickly. So, so we have phi of G here. Then we had pi Pn in this guy. Then we had phi of G, times for Fs. Then here from the definition, I get pi Pn, and then basically phi of G. So that's what I get. I'm just inserting the definitions that we have. And now, okay, I'm kind of jumping the gun a little bit because in order to prove this, I need to already know that there's an equivalence relation that's, I can replace fs by this here without losing any information, which can separately prove, which I haven't done here. But I don't want to prove it separately because I'll lose too much time on this. I mean, this here, this is clear. This is here pi s phys G. And yeah, so here I do need, this is something I didn't prove, but basically here I need that I can just replace the fs by this guy without losing any information. So you just have to take my word for it. So we can here just replace this without losing any information. So we have an additional pi phys here, and then you have pi s phys G. Okay, and then there's a little bit of gymnastics. Then you have this phi G phys. Okay, maybe I should not have started to prove this because it's costing me time now. It's really not very hard to prove these things, but so I have this part and I have pi Pn, phi of G, R. And then I recall the definition of this guy, okay. Then you can convince yourself that that this collapses in the claimed result. So I think that's an exercise for you because time's running out. so what you have to do is just insert the definition of what this highest fizz is, and then play around a little and see that this is true. And I think the converse direction is probably immediate. That in this case, yeah, here you see I will get a pi fizz here. I will get one part of the conditioning, I get the other part of the conditioning which goes past this. So this actually can get this kind of trivial. So it's trivial. And then, that this result follows, then it's just by unitary, it's clear, it's just the inversion of it. Okay. So so maybe if you have nodes here, then I'll put here exercise. Okay, so far so good. What I now want to do is come back to yeah. Let's say we have some R1. We just write R1 of G. So suppose we have H kinematical as H1, H2, and then the system again. And now assume R1 is ideal. Right, ideal. So we assume this. So this means that the corresponding projector is trivial. Okay. So this means that here the image I get to tensor HS. This is H2S fizz is actually equal to that. Right. So whatever I had here when I only did an RS split, what was the system here is now. When I do R1, R2S relative to the choice R1, what was S before is now R2S. Okay, so that's why I have 2S here. And here I'm just using that for ideal on reference frames. This is trivial, this projector. So that means the image or the perspective of the quantum reference frame 1 is in this case is really just a tensor product of the kinematic Hilbert spaces for its complement. And now, well, for simplicity, let's assume also that this is that we have an R2. So then here in this case, we have 1S is equal to this. So now I'm coming to these statements about tensor product structures. So we've shown that this is a unitary, and I'm mapping an abstract Hilbert space to a tensor product. So R1 is a unitary mapping HPN to a tensor product. And a tensor product structure is an equivalence class of such unitaries. So you have that R1 is equivalent to R1 prime if R1 prime dagger is a multi-local unitary, or you can also have a swap of equidimensional Hilbert spaces. In our case, the latter is not so important. And so now the point is that what do we want to check? So we have that R1 of G, in fact, is equivalent to R1 of G prime for all G prime. So that tells us that I do different gauge fixings. It defines the same tensor product structure. They're both part of the same equivalence class. And really the way to see this is that, maybe write it like this, so G prime G. This is phi of G prime G, R. But, okay, maybe I'm going to insert here, sorry, maybe let me just, to make it clearer, for simplicity, for clarity, I'm going to act on physical states. And now I'm going to make use of the covariance of the reference frame orientation state. So I can pull out the UG R prime, right? So this is, actually, sorry, here, this should be a 1 and this here should be 2s. Okay, so there's 2 of these guys. So this here I can write as phi of G R1, and then U R1 dagger of G prime, and then I2s, and then psi. But now I can again make use of the invariance of this psi. So this here is just UR1 G prime inverse, and I hit this guy with it, and then I bounce off a UR2 of G prime and times the US of G prime. Okay, so this is equal to U2 of G prime tensor US of G prime acting on R1 G psi. So that means, so this shows that they're equivalent because they're related by a multi-local unitary. So this means an ideal QRF perspective by that I mean really this reduction map, because that's one way of defining a perspective, is a tensor product structure on HPN. So this is important here because it tells you that, I mean, of course, it's a gauge invariant Hilbert space. If I have a tensor product structure, it should be gauge invariant. So it should depend on the gauge that I use to define it. And this is here what tells you that that's indeed the case. So for whatever gauge I pick, I have the same tensor product structure, because whatever gauge I pick, they both lie, these unitary maps, the reduction maps, lie in the same equivalence relation, so they define the same tensor product structure. So this is a somewhat subtle point, but it's quite important. So really, one thing you have to note is that the choice of quantum reference frame is not a choice of gauge. Okay? You can think about it as it is a choice of degrees of freedom I might gauge fix, but it's not a choice of how you gauge fix it. So rather, the choice of quantum reference frame is a bit akin to the choice of Lorentz frame in special relativity. It's not a gauge choice, it's just a convention you make. And here, this is fully consistent with the choice of quantum reference frame. It defines me a gauge invariant tensor product structure on the gauge invariant Hilbert space. And yeah, it does not depend on the gauge. So this is quite important. yeah, so this is kind of important. And then, of course, the same here is true with this one, right? So this being an ideal quantum reference frame, that's another tensor product structure, another gauging around tensor product structure of this Hilbert space. And so in particular, what that tells you is that changes between ideal QRFs are changes of tensor product structure on HPN. Yeah.
Just the equivalence relation R1 dagger is equal to what? What does that say?
Here? No, here?
Just slightly above that. When you're defining the equivalent.
Oh, sorry. I'm just kind of in words. It's equal to multi-local unitaries, or in quotation marks, or in bracket, it can also be swap of equal dimensional tensor factors. But here in this case, that's not happening. So, so I mean, this is just a mathematical definition of tensor product structures on a Hilbert space. So you can look that up. So in this way, you see that really Page-Wooler's reduction is nothing else than a tensor product structure. So that tells you also, okay, a choice of quantum reference frame is a choice of gauge invariant subsystem partition. And now, so I will not have time to discuss this. That's what 10 to 3. For non-ideal QRFs, we have that I as phys is not equal to the identity on S, so it will be a non-trivial projector. It means for non-ideal quantum reference frames, I will map to subspaces of this. Okay? So I'll have that, for instance, R1G, HPN is, well, here I guess in this case I should really write still 2S, right? So I have 2 with S phys G and active S. And now in general, this is a non-local projector, so it's really a subspace. The image of this is going to be a subspace of this tensor product structure, which does not inherit this tensor product structure. There are cases, there can be special cases when this projector actually factorizes, and you will actually still have a tensor product structure of subspaces, but generically that's not the case. But then typically, you can write this right-hand side as a direct sum or a direct integral of tensor product structures. Just kind of write this like this. We don't really have a lot of time, so I'm just going to write it like that in sort of schematic ways. So in that sense, you can still think of this. So it's still a gauge invariant subsystem partition. But it's a more complicated one. It's just a more general one because you have, in simple cases. So if you do this for finite groups or so, or compact groups, then you will have some direct sum. So you have a direct sum of tensor products. When the group is non-compact, then typically you'll have a direct integral, so it gets a little bit more complicated. Okay. So that's why, in general, you can still think of really, in general, so QRF changes are changes of subsystem partitions. And here it's really important that the subsystem partitions that we're talking about are internally defined ones. So they're defined relative to an internal reference frame. They're not the ones relative to the external reference frame. So in general, the internal reference frames, what they identify as different subsystems is not what the external reference frame will identify as different subsystems. So it's really, quantum reference frames are the way to define gauge invariant notions of subsystems. So here I've described this in terms of unitaries. You can do this also directly at the level of gauge invariant observable algebras. So, so I think that part I'm now not going to prove. It's maybe I'll give you a bit of intuition for it. Just for time reasons, I will probably skip that. But yeah, in general, you have basically two or more equivalent ways of defining a tensor product structure, and the algebraic way is that so an alternative, really an equivalent definition of the TPS. You have a set of algebras, call them A alpha and alpha in some index set, such that, write in green now, such that I alpha A beta is 0 for alpha not beta, so they commute. Then that A alpha intersected with A beta is just C times the identity, so it's just the identity component. And that if I take the join of all these algebras, so I get okay, the full algebra in whatever the Hilbert space is. So for instance, let's say we take the full sort of bounded operators in the Hilbert space. So this is another way in which you can think about a tensor product structure. And here, in our case, this is also realized. Here, for instance, what you will get, then if this is true, then you can write basically this B of H, you can write it as a tensor product of I as such. And here, indeed, we will have that the perspective neutral algebra, for the case of ideal frames, I should say again. So ideal QFs, you can write it as, so I'm still in the case where we have 3 subsystems, so 2 frames and a system, that this is R2 relative to R1.
Excuse me.
Yes.
Would you change the color of the...
Oh, is that hard to read? I'm sorry. Do you want me to write this again, or is it?
Yeah, I can.
Okay. So it's R1, R2, tensor S relative to R2. But you can also write it as a R2 relative to R1. So I'm going to say in a minute what this is. AS relative to R1. So these are the algebras of relational observables, describing the first frame relative to the second, system relative to the second frame relative to the first, system relative to the first. So when you have ideal quantum reference frames, you can decompose the algebra. So here, where APN is, for instance, the set of bounded operators on the perspective neutral space, then you can decompose it in this way, for instance. will satisfy these conditions. And here I'm putting a tilde on it just to emphasize that that tensor product here is a different one than that. Okay. So in particular, the relational observables describing S relative to R1 and S relative to R2 are not the same algebra. They could in principle be isomorphic, but they're different subalgebras. So can show, can give you the references that A S relative to 1 is intersected with AS relative to the second is it is the system algebra, the G invariant system algebra, and then I'm going to write it like this for now, restricted to the physical grid space. So that is the only thing that reference frame 1 and reference frame 2 agree on about the system is what is already gauge invariant without addressing to the frame. So this is G invariant S algebra. But of course, in general, the G invariant S algebra is a non-trivial subalgebra of the system. So in particular, if the system is sufficiently complex, this can be quite a non-trivial algebra. But in general, of course, it's not the full algebra. So that tells you really that these guys are not equal to one another. So that tells you that neither these are equal to one another, so the tensor products are also not the same. And so this is subsystem relativity. So I'm just going to draw this schematically. So this is kind of important because this is, call this UPN, because this is essentially the whole crux of quantum reference frames. That's why it's we kind of need to understand this. So you can, so this is just a schematic representation. So we can think about, we think of this algebra, the total gauge invariant algebra of the physical Hilbert space or the respective root Hilbert space. So let's say this here is AS relative to R1. It's a subalgebra of the total invariant algebra. And then you can think about, the exact geometry of what I'm drawing here should take two series, of course. It's really just schematic. And let's say AS relative to 2. And then, okay, we have this overlap. Okay, so the overlap is black. And this here is ASG restricted to the perspective Hilbert space. So in particular, this subalgebra here that sits in the intersection, it is the internal relational observables within the system. So if the system is sufficiently complex, you can have another set of reference frames inside the system, and you're just stressing the system with respect to degrees of freedom on the inside. Okay? These are sort of internal relational observables of inside S. So gauge invariant without addressing to R1 or R2. So it's not very hard to show this. So can I get 5 minutes and maybe I'll just give you the intuition behind this. So you get something similar also for non-ideal frames. It's a little bit more subtle in that case. Because of this non-trivial projector, when you take subalgebras of the kinematic algebra for the complementary frame in the system and you project each one of them with this projector, in general, it is not an algebra, that thing. So you have to be a bit more careful in that case. And I don't have time to discuss that here. You can also handle it, but here, for simplicity, I take the simplest case where it's ideal. Yeah, maybe let me first give you the intuition for this, and then we can, and then I make a final comment in relation to my opening statements of the lectures, because I was talking about what's the equivalent of relativity of simultaneity for quantum reference frames. It's actually this subsystem relativity. So the intuition is basically, so you have a bunch of balls, and let's say, this here, call that the system. This is R1. No, I guess that's R2 if I want to. Okay, no, the colors are inconsistent anyway, so. All this R1. So the picture that we see here on the blackboard from your point of view is basically that of the external reference frame. It's the sort of kinematic or subsystem partition. Now, that there is a difference between the kinematic or subsystem partition, so what you see and what an internal reference frame will see is immediate from the fact that, for instance, I can take this first reference frame, I can do a reorientation. We know it's a physical symmetry. So I can move R1 here without doing anything to the rest. So here I just do some R1G. It's a physical transformation. Clearly, relative to you, nothing has happened to the system. But the description of the system relative to R1 has changed because the relation has changed between R1 and the system. So this is immediately how we can see that the internal description of a subsystem is very different from an external description. And now, of course, I can also do the same thing that I, in particular, if I do this here, that you can immediately see that also the description of the system relative to R2 has not changed, because the relation has not changed. So in this way, you can see that the description that R1 and R2 will associate with the system, they must be different. So it's a conceptual way, like a pictorial way of seeing that it has to be different. Now, of course, I can also, do some reorientation of the second frame without doing anything to the rest, and that will change the description of the relation between R2 and the system, but it will not change the relation between the first frame and the system. So in this way, you can see that, get some intuition that the description, of course, that's the external frame associates with the system, and that what the two internal frames associate with the system are all three different ones. And now you can note, well, if I reorient the first reference frame, as I said, then the description of S relative to R2 shouldn't change. And indeed, if I take the relational observables that describe the system relative to the second reference frame, and I do a reorientation with respect to the first reference frame, it just commutes, nothing happens. They're invariant under this. And similarly, the observables that describe the system relative to the first one, they're invariant under reorientations of the second reference frame. So that tells you that whatever lies in the intersection of the two algebras of relational observables must be invariant under reorientations of both frames. Okay, and then you can kind of very quickly, so this is the main insight, and then you just check with the expressions of the relational observables what is invariant under all reorientations, and then you immediately arrive at okay, the system has to be invariant, the system observables. Okay. So main insight is so observables in this intersection AS are 1 phys and AS 2 phys. So this is of course kind of a hand-wavy argument that I'm making, but the point is you can make this precise. Must be invariant under reorientations of both R1 and R2, and if you make use of this, you arrive at that. So, so this really tells you that so this is subsystem relativity. Two different quantum reference frames decompose the total gauge invariant algebra on the perspective neutral Hilbert space in different ways into what they call system and the other reference frame. So that is very analogous to the relativity of simultaneity, where you have two inertial observers that decompose space-time in different ways into what they call each space and time. And now it turns out that actually there's a relation between the two. So I described to you special relativity with inertial reference frames, with internal reference frames. And you can do the exact same thing that I'm doing here for quantum reference frames, you can do with tetrads also in special relativity. You will find the exact same structure. And then the point is also that in that case here, what I also forgot to say, so this is ideal quantum reference frames. The transformation that takes this algebra into the other algebra is exactly this, this kind of Pascal, that I described today at the beginning. So that transformation that takes one bar into the other we've described. If you do it for special relativity, the thing that does the analogous thing is this, what we had, this lambda, whatever, B prime A or something that we had. So the point is, it is in that case also a Lorentz transformation, and it is really that frame transformation that encodes, of course, in actually the relativity of simultaneity. So in that sense, if you do this for special relativity with tetrads, you get subsystem relativity, and that subsystem relativity actually encodes the relativity of simultaneity. And so in that sense, you can really view subsystem relativity as the natural generalization of the relativity of simultaneity. And so in the very beginning of the lectures, when I was giving Galilean relativity, special relativity, general relativity, quantum relativity, what's the analog? What do different quantum reference frames decompose in different ways? That's the analog of, for instance, relativity of simultaneity. It's a subsystem relativity. And really, you should view it really for quantum reference frame covariance, really in the same spirit as you view the relativity of simultaneity in special relativity. It is the source of all the counterintuitive phenomena that you have in special relativity. It's the source of Lorentz contractions, of time dilation, blah, blah, blah. You can actually derive all of that from the relativity of simultaneity. In the same way, here with quantum reference frames, everything about quantum reference frame covariance follows from this. So what I showed you before, that with this kind of simple transformation for three particles on the line, product state to entangled state, well, it's subsystem relativity, it's in play there. Right? So in that case, one particle and the other particle, they mean different subalgebras when they refer to the third particle. So, and that's why, of course, when you use the different relational observables in the same gauge invariant physical states, the correlations you measure will be different. Okay? So it all boils down to subsystem relativity. And so I was going to explain a little bit more about this, but I'm going to cancel that part about how this implies also the relational notion of thermodynamics, quantum thermodynamics. This also implies, so we did a systematic analysis of this, of thermality of states. For instance, if you have Gibbs states on the system in general, thermal equilibrium will be mapped to non-equilibrium. You can use quantum reference frame transformations to change the temperature of the equilibrium. You can even change the sign of the temperature when you have bounded Hamiltonians in both directions. You can look at entropy productions and all those kind of stuff, and check very systematically how this depends on the choice of quantum reference frame. And of course, one quintessential thing that will be in general dependent on the choice of quantum reference frame is also entanglement entropies associated with the system. Okay? And one important thing is that these quantum reference frame transformations that I described are unitaries on the global Hilbert space, on the full when I apply it to the full Hilbert space, right? I mean, not the kinematical one, but the perspective neutral one, and then the internal frame perspectives. But that, of course, doesn't apply that when I look at density matrices for the system, then on the system alone it will be unitary. And of course, in general, it's not because of this here. And that's why if I look at a density operator for the system in one frame perspective, and I look at what's the corresponding one in the other perspective, they're not unitarily related in the general case. You can actually, in finite dimensions, classify exactly when they're unitarily related, so that's what we've done, but the generic cases they're not. And anyway, so, okay, it was a little bit technical and some of this was kind of abstract, but I just want you to see that this is a general result that we have here. It's not special to any examples really, it's really the crux of the whole game in some sense. And yeah, it has a lot of physical implications that, okay, some of which here I just mentioned in words. I don't have time to discuss it. But then later today, I will try to jump into relational entanglement entropies for an input type of quantum gravity, which will be just an application of this.
Is there a reference?
Yeah, so the reference for this stuff here, so the most systematic reference analysis of thermodynamics, correlations, and so on is in this 2308 one that I already gave you. So that one is actually in finite dimensions. This is it's a pretty long paper. 09131. 09131. So there is also in other papers, for instance, lattice gauge theories and some of the stuff that we did recently. I mean, in the subsystem relativity appears in really a lot of quantum reference frame papers now because that's the heart of it. The first paper is a PRL. It's published in 22, and it's Ahmad et al. It's called Quantum Relativity of Subsystems. So I'm one of the authors on that one. But really, I would rather recommend you this one here. This comes later, more than 2 years later, and the perspective that's described in there is much more didactical and systematic. So, okay, any questions on this for now? So yeah, then after the break, I'll start switching topics and more applications. So for the moment, we've just done formalism. Okay, we'll do some applications later from now on.
So, no question? So I guess not. Then let's thank Philipp.